Right, this is class 3, and we're just going to wrap up climate change really quick in the first 20 minutes, hopefully. We might get into a little bit of discussion, but I'd like to move through this. So if you do have any pressing questions, feel free to ask after class or email. And then we're going to dive into energy. And you do have an exam that will be open to you on Moodle starting Thursday this week. That's mostly about the energy side, not the climate side, so we should get into that soon. So we kind of ended here last week with Senator Snowball from Oklahoma, and we were talking about the greenhouse effect, so just a quick review. Greenhouse effect, obviously a natural thing. This is what keeps us alive on this planet. And if you want an example of what the extremes would look like with or without the greenhouse effect, you just have to look at our two closest neighbors. Mars has a very, very thin atmosphere and not much in the way of greenhouse gases, so it can't trap the sun's heat very well. And so most of what hits Mars ends up being radiated back out into space. Opposite end of the spectrum, Venus is a runaway greenhouse effect, where its atmosphere is almost entirely greenhouse gases. And if either one of these planets had Earth's atmosphere, they would be on kind of the verge of habitable. They would actually be able to survive their temperature. So it's not so much the proximity to the sun for these three planets as it is the atmospheric composition that makes them warm or cold, or in the Goldilocks zone. So regarding the greenhouse effect, this happens all the time, but what we're doing is this part right here. We're increasing the part of the atmosphere that's just good at absorption. And we can see this pretty clearly in the data, the increase in carbon dioxide especially. And it's something that has historically been true. Carbon comes and goes as the planet changes. The issue right now is that we're doing it so quickly, the Earth can't respond. So there's always the question, what are the effects? It's really hard to gauge. You know, the world has agreed, as you just asked earlier, the world has agreed as a global population that we will accept 2 degrees Celsius rise in temperature and nothing beyond that. But what does that even mean? I mean, 2 degrees, which would be about 4 degrees Fahrenheit, if you want a comparison. That's not a huge change, right? In the time since this class started till now, it's probably gone up 4 degrees outside. We can handle that. Yeah, I hope so. Kind of cool. So why would a 2 degree Celsius rise in temperature really matter?
Because it's a global average, so that's kind of all of the global temperature rises in different areas and combining that data and dividing it out. So 2 degrees overall really means like 20 degrees one place. So it does mean that there's a huge temperature change happening in each individual area. 2 degrees is just...
Yeah, it's certainly a big part of it.
It also affects countless number of ecology. Animals are dependent on the environment to survive, and whereas humans tend to rely more on their condition while they're inside their homes, they don't really notice too much of a difference. They, on the fringes of civilization, see where it starts to break.
Yeah, and that's especially the first part of what you just said is key. It's humans are amazingly adept. We can survive in all kinds of climates, but every other species on the planet can't. So if you look at this list of effects up here, we've got these categories on the left: food, water, ecosystems, weather events, and what I will just term feedback loops on the bottom. And you can see even with a 0.3, 0.5 degree rise, the food system starts to change. And it's not because we are changing. It's because the little biota in the soil and all this stuff, it really makes a difference for those species. So a 2 degree rise is massive for everything else on the planet.
I think I already said this before too, but I just think of it as like my body, and like if I get like a fever and it's like 4 degrees Fahrenheit over 2.
Yeah.
So it's like, and then you think of like that Earth, which is like a body really, but it's a lot changed.
That's a great analogy. Yeah, a lot of people would describe global climate change as a fever. The fever is meant to purge your body, right?
Yeah, and that's
That's
like
right.
what it's trying to do.
Yeah, if you want to think of kind of anthropomorphize the Earth as a conscious being, it's sort of running a fever, trying to get rid of it. Yeah, we don't want to go down that road too far. It tends to get a little woo-woo in there, but yeah, essentially what the Earth is having. So this vertical orange line, just shy of 1 degree Celsius, that's where we already are. So the 0 degree would be pre-industrial temperature averages, and those are long-term centennial averages. We're already 0.8 to 0.9 above that. And so we're already starting to see some of these effects that you can see in the arrows. So the northern hemisphere, Russia, Canada, the US, we're starting to see longer growing seasons, which many would see as a positive. But you're also starting to see horrible effects closer to the equator, the Sahel region in Africa, the desert, like greater desertification of the Sahara into the Sahel, all these things. Coral reef bleaching and death. We've already seen about 90% of global reefs are bleached, and about 35% are dead. Just in the past 10, 20 years. Something you couldn't even imagine as a kid looking at National Geographic pictures of the Great Barrier Reef. It's now white. So the question is, where are we going to end up? Where are we headed? If we can stop at 2, we're still committed to a lot of these negative effects, but maybe they're manageable. Like that. If we get beyond 2, it's hard to tell what happens. So we do have models that try to predict where we're going to be at a certain time. And the models I'm going to show right now are predicting what the temperature rise will be by the end of this century, 21. Probably none of us will be alive. Hope not. We might, in which case, good for you. Bad for you. We'll find out. And it depends which model you use. It's hard to write climate models because you're trying to model the entire planet, which is hard to do in Excel. They're not using Excel. The more optimistic models put us at about 3.5. And this is if we continue with business as usual. So the rate at which we're integrating renewables, the rate at which we're increasing industry, the rate at which we're electrifying, that's what these are assuming. So 3.5, you can already see we're committed to almost everything in terms of the negative effects, just if we keep the status quo. The average model puts us at about a little over 5. You can see we've committed to all of it. And then the more pessimistic, or what's turning out to be the case, is the most accurate, the most consistently predicted models that match reality put us closer to 7 or 8 degree rise in temperature. Which, back to the fever analogy, if you raised your body temperature 8 degrees Fahrenheit, you'd be dead. 8 degrees Celsius, you'd be double dead.
Yeah.
Double dead. It's a real thing.
But I mean, we're on the kind of starting to decline though, right? Weren't we talking about that last week?
In terms of emissions,
Mm-hmm.
no. We're starting to level,
Okay.
and certain countries are starting to decline per capita, but everyone else is increasing.
Okay.
So the U.S. is still increasing its emissions, but we're declining per capita.
Okay.
Or we're starting to
Okay,
decline
that's what. Yeah.
per capita per person.
Yeah.
Gotcha.
Thanks for clarifying.
Totally.
Yeah.
Got it.
The European Union and Britain, thanks Brexit, is also declining per person, but everywhere else in the world is increasing quickly. So
Things aren't so grim. India's energy minister decided to be the leading head in solar technology over there in the eastern part of the world.
Down in South America, some country just went over 100 days.
Uruguay.
Yeah. Was it who completely self-sufficient?
Costa Rica.
Oh, just producing their own energy.
Yeah, producing
Yeah.
their own.
Costa Rica's
I
pretty
think it's
good.
like 100 and something days.
Okay. Yeah. A lot of countries are really doing it. Iceland's been doing it for
Oh,
decades.
yeah.
Just think if these places
I love
got
Iceland.
publicity, that would spread throughout a functional and feasible way of doing things.
Also keep in mind, a lot of these countries aren't 100% electrified, so there are still populations not getting energy, and the resources they have
So
matter.
here's a question. Is there any news environmental sustainability?
350 is pretty good.
350 Missoula?
350.org.
Oh, those are international.
Yeah.
Yeah, that's right. Okay, yeah.
And they're definitely, they have a bent, they have an agenda, but they're really good at this. They're good at reporting the positive news.
That's good. That's what I'm.
But what you'll learn in this class is how to critique that news, because the way they word things matters. So like saying we're declining in our emissions. It's like, well, who's we? What does declining mean?
And what kind of emissions?
What kind of emissions? Yeah, so to say, yeah, the U.S. is declining emissions, yeah, per person and in some sectors. But also there's these other things.
And corporations are people too.
Yeah, there's a lot more at stake, so that's what this class is for.
All right, awesome.
But what I wanted to get to is this, that you can see all these negative effects, these arrows kind of going to the right. The fun part about this is that with these models over here on the far right predicting 7.4, this is all gray for a reason. It's because we have no clue.
So
What happens.
could be happy.
This could be a little utopia over here.
Yeah.
We're like, who knew? We wanted it to be.
Hell on earth.
But the thing is,
Let's
when
migrate
you,
to Antarctica and it will be paradise.
yeah, exactly, yeah, lovely. Without the ozone layer, it's very good. So entire regions experience major declines, strong carbon fertilization, sea level rise, all this stuff. Once all this happens, we don't know what happens to human society. Because once you threaten food security, water security, and you kind of flood all the coastal zones where 80% of the human population lives,
I can imagine.
we don't know what happens.
Are we good?
Yeah, it's going to be a Kevin Costner movie. It's kind of that's this gray area. So that's not to be like a doom and gloom thing, but we literally don't know what this looks like. So I'm going to move on from that. Enough negativity. Just wanted to give a quick, fun kind of comparison with emissions by country. So this is total emissions, not per person. So you can kind of see the usual suspects: the U.S., Canada, Brazil, Russia, China, India, Australia, Saudi Arabia, Nigeria, South Africa. The industrialized Europe. It changes a bit when you go per person. So suddenly, Canada's worse than the U.S. Kazakhstan is worse than Europe. But there's some fun little examples in here. If we go back up to this one, down here in southern Africa, we can see that South Africa is kind of the major player. Everything else is kind of average or pretty low. If we go per person, boom, Zambia pops out. Why Zambia? All you world travelers.
Is there like a higher standard?
No, it's one of the poorest.
How do they use?
How do they use more energy? Mining. Where does our copper come from?
Oh, really?
Zambia.
Really?
Yeah, it used to be Montana.
Yeah.
And you can imagine Zambia doesn't have much better environmental regulation. And it's not Zambia doing the mining, it's colonial powers doing the mining, Zambians doing work. So they use a ton of energy just for mining, but they don't necessarily reap the benefits. Another fun example, Indonesia over here, this big archipelago, a lot higher than Malaysia, which is sitting on top of it. And if we go to per capita,
So this isn't really.
yeah, it's switching. So Indonesia has a lot of emissions, Malaysia not so much, but if you go to per person, Malaysia is just as bad as the U.S. per person. Because it's one of the Asian tigers. It developed way faster than Indonesia.
One of the what?
Asian tigers, it's the term used to describe the rapidly developing Asian countries. Same thing if we go back, Indonesia again, high emitter, Papua New Guinea, not a whole lot going on. Per person,
Wow.
Papua New Guinea. Wow. Similar thing is what's going on in Zambia. So you can see a lot going on. You can read so much into the energy world just by comparing these two maps. You can almost see geopolitics just happening in front of you. I just did that because I like maps. There's really no other reason I brought that up. Sorry, those of you online. I hope you like maps. So, quick, summary of emissions, or I guess sources of greenhouse gas. This always comes up. Well, there's a lot of things that produce greenhouse gases. There's agriculture, there's cement making, there's deforestation. So historically, what have been the active emissions? So you can see deforestation since pre-industrial times has been a big player, since we use wood for everything. You can see the rise of the British Empire through the late 1800s, and the rise of the Industrial Revolution, coal. And then you can see the rise of the American Empire in the oil addition, and then with the gas addition. And so, if you're ever wondering, where do these emissions come from? There it is.
What was that spike like right before 2000?
Yeah, I see that spike there.
Yeah, so what's the fundamental base of the spike? Is the spike in gas, in oil, in coal, in
I mean,
deforestation?
it seems like it affects all.
It affects all of them, but what causes it? Where did the spike start?
Deforestation.
Deforestation, yeah. So if you took away this deforestation spike down here, all these spikes above it would disappear. So deforestation is the spike. Anyone know what that was? It was Brazil's massive push in the late 90s to deforest the Amazon.
Oh.
And then they got a huge slap on their wrist. Yes.
It looks like we really started climbing right around the same time.
Yeah, well, that was post-World War II. That was the rise of the American middle class, European middle
Baby
class,
boomers.
baby boomers. Yeah, that was it. The other question that always comes up, well, what about the natural causes of climate change? And these are real. Don't discount them. But they're not always as big or even in the direction that people think they are. So a big one is solar spots and increased solar radiation. Solar spots, the people who claim solar spots really don't know what solar spots are. So make sure you get them to explain what solar spots are. Or sunspots. The sun's energy output has increased since pre-industrial times. It does that from time to time, kind of wavers back and forth. But it's not a whole lot. You know, a fraction of a degree is what that would cause. Land use changes are certainly a real thing, but again, not a big change. Aerosols from urban pollution and aerosols from volcanic venting. Aerosol just means particulate matter in the atmosphere. That actually has a cooling effect because most of these aerosols are actually reflective. So once they're in the atmosphere, they actually reflect a lot of the energy back out into space. So a volcanic eruption would actually cool down.
Haven't they thought about doing that? Or like talked about it at least? Like just setting off.
Doing it already?
Setting off
Chemtrails.
a volcano.
Are you serious? Yeah, that is.
Geoengineering.
Just to like set the
Conspiracy
flame.
theory.
Yeah, they're
No,
talking
it's
about
totally-
releasing aerosols,
They've actually
specifically
looked at
sulfur
it.
dioxide.
I've seen
Yeah,
the
It's really
buildings.
good. So
Yeah.
geoengineering.
Would that be like once we get to the point of like 7 degrees? Or would it be sooner than that when we're over like the 2 degrees?
Where's that place in Alaska?
It's a proposal right now. I think the proposal is to do it right now.
Yeah, that's really
Pretty
cool.
much.
Yeah.
But who knows what other.
We need
I'm
to
on
change
board. I
it
watched it
before
all.
we try to stop it.
Sounds like it would be a huge beast plant or something.
Yeah.
Just
You
set
should get
off-
on that.
Set off Yellowstone and then you do
All right, everyone heard that. If all the volcanoes erupt at one time,
it.
that's the guy who probably did it. I have this plan. It's gonna be great.
So, would it be a thank you, not a?
It depends if you're the one at the
Let's do
volcano.
just enough just to make everybody happy.
But I bring this up because there are natural effects that do cause our climate to shift. I mean, we saw that graph earlier where temperature was going up and down the last 400,000. That's because it's a real thing. But you can see very clearly the only emission source, or the only factor that really predicts or causes us to follow the trajectory we have been going on, is the heat-trapping emissions, the greenhouse gases. So that's how we know it is greenhouse gases specifically that are causing this climate change, whereas other things have caused other. Is that kind of? So yeah, the aerosol question, the geoengineering thing. There's all tons of articles about
Yeah.
that and the different.
Yeah, I actually just heard about it.
There's also proposals to put giant mirrors in space between us and the sun. No, we're kind of desperate at this point. So it's like
That's what it comes down to.
whatever works. There's also kind of not directly climate related environmental effects of energy or environmental factors related to. One of the things you have probably already discovered and will discover more in this class is that it's a giant nexus. What we typically term the food, energy, water nexus. These things are inherently related. If you change one, you're affecting the others. So I won't bring up food because I think you can probably figure that one out. But water and energy are hand in hand. So just to give you some fun stats, 50% of global freshwater withdrawals are for energy. That's energy generation, energy transportation. So when you talk about water security, only 85% of that is for drinking, for washing, for irrigation. There's a lot more going on. Thermal power plants use almost half of the water withdrawn in the United States. So thermal power plants, that's coal and gas primarily, but also include nuclear sometimes, depending on the year.
Why don't they use, or is that fresh water, or?
Yeah, you can't use salt water.
Well, what if they like did the desalination?
So desalination requires more energy
Then
than you would get by supplying that fresh water to a plant.
yeah.
So does it contaminate the water? Maybe, basically.
It depends on the power plant. So some power plants, and you learn about this, have open loop systems where you bring water in from a river, run it through your power plant, create steam, turn turbines and all that, and then dump it back in the river.
Yeah.
It doesn't necessarily contaminate it, but it warms it up, and that harms the ecosystem down there. Because warming water in a river is not doing it that quickly is not good. Other power plants are closed loop systems where you bring in water from a river just as coolant to cool down the steam that's in another closed loop, and then you dump that water back. So either way, you're warming it up, but it's rare that you would be contaminating it.
Really?
The only times you would contaminate water is if it's a really inefficient coal-fired power plant, or if it's nuclear.
Yeah.
And in nuclear power plants, it's always closed. They don't release that water.
You don't.
No, that's it.
But that releases it.
No,
Really?
that water stays in the loop.
But nuclear power plants release steam to cool their reactors, so.
That's coolant water. So yeah,
Does
that water.
would be the water that comes through and goes back.
Right. So there's a water loop it's water. It's heated up by the nuclear reactor. Comes steam from the turbine. It's cooled down. This water again just keeps going on with that. It
Okay.
keeps becoming steam, water, steam.
It still
What
leaves the
It'll
loop
evaporate at
via
some point.
steam, and then
Nope. Well,
that it creates some acidity. Yes, that's where acid rain comes.
nope.
That is true.
We're getting a little bit far from where we were. That loop stays closed unless there's leakage, which would be a problem. The water that cools it down comes from outside, cools it down just through a heat. Heat exchanger, where you just like touch the pipes together, so the temperature can change, but the water doesn't go between. And then that water goes to the cooling towers, which evaporates. So that's the steam you see coming out of a nuclear power. That's the cooling tower.
It's passed through all the reactors and all that stuff. and
No,
then
it hasn't touched the reactors.
So just through pipes?
It's just through pipes. So it comes out of the river, it
Oh,
passes by the pipes to cool it down.
Pipes rope.
Thanks for it.
Yeah. I mean, that's the issue with nuclear is a lot of people don't understand exactly what's going on inside. It's just a big black box. And we know there's something nasty in there.
Steam coming out of there.
We see a bunch of steam coming out. It's just cool. So you're welcome to not know until you've taken this class, and then you should know. And you have no excuse not to know. Yeah. Last water stat in California, water-related energy use consumes 20% of the state. So these may seem like random stats, but if you put them all together, what you have is energy you need, the more water you need. The more water you need, the more energy. And so if you're inefficient in your water, your energy system, you have to use more of the other. But it also means if you increase efficiency in your water system or in your energy system, you increase your efficiency in the other as well. So it can be a positive or a negative feedback. They talk about water, think about energy. They talk about energy. All right. Oh, do you guys still need that? Okay. I'm going to stop this video here. We'll cut this and then we'll go into video 2 and we'll start in on energy itself. Find this. Here we go.